So let us now launch into looking at atomic structure, what an atom is made of and how we represent it with isotope notation. So what does the atom contain? Well, principally two main areas, the central nucleus in the centre and the surrounding electron cloud. So the nucleus is where we find the protons and the neutrons. One element to another will have a different number of protons, and the number of neutrons may change also. Characteristically, the nucleus is very dense and the whole thing carries a positive charge. Around the outside, there are the electrons that exist in various different energy levels or shells. Now, the nucleus is 10,000 times smaller than the atom itself. It means that really if an atom was the size of a large football stadium, the nucleus would be no larger than a pea. So in all of our diagrams, we're going to now draw atoms basically made out of three types of particle: the proton, the neutron, and the electron. Now, if we compare the properties of these three different subatomic particles, you start to see a pattern. That the proton and neutron are very similar in terms of mass. If we were to measure their relative mass, then we give them a relative mass of 1, whereas an electron has a relative mass much smaller. In fact, it is about 1/2000th of the mass of a proton, which means that I could get 2,000 electrons on one side of the scale before I balanced out a single proton on the other. If we look at the charge, well, a proton has a charge, we say, of +1, and the electron has a charge of exactly -1, so that the charges would cancel out if I had a proton and an electron. The neutron has no charge. If I had one atom and it varied from the next only in the number of protons it had, then what we would say is different is that it is a different element. If we had two atoms identical in every other way, but different in the number of neutrons that it has, we would say that that is a different isotope. And if it was identical in every way, but it was the number of electrons that changed, it would be a different ion. It's possible to have positive or negative ions. It all depends on whether or not there are more negative charges than positive charges. Normally, a neutral atom has exactly the same amount of positive charge as negative charge, resulting in an overall charge of 0. Since the time of John Dalton, we have been representing the elements by a symbol notation. Every different element could be represented by a chemical symbol. Now, we don't use the same that Dalton did. We use a chemical symbol that derives either from its English or its Latin name. In many elements, this is a single letter. Like, for example, hydrogen is represented by capital H, carbon is C, nitrogen N, and oxygen is O. Occasionally, where more than one element exists that begins with the same letter, a second letter is brought in. Like, for example, we couldn't call helium H because hydrogen is H. So we call helium He with a capital H and a lowercase e. Other examples include Li for lithium, Be for beryllium, and Ne for neon. A really handy way of identifying on paper whether or not we're talking about this element or this isotope or this ion compared to another one is through something called isotope notation. And it looks a little bit like this. Here we've got a general formula, which basically means the X represents whatever chemical symbol you want to put there. So if we were talking about hydrogen, we'd replace X with a H. If we were talking about boron, we'd replace the X with the B. Now next to this, and on the left-hand side, we have a superscript and a subscript. You can see here, in the superscript position, the letter A. Now this stands for the mass number of this particular atom. So in the example on the right-hand side of nitrogen, nitrogen 14, you can see it has a mass number of 14. This tells you the total atomic mass of this atom. So in the nucleus, we have 14 protons and neutrons together. The number that is subscript at the bottom, the Z, is the atomic number. And this tells us either the amount of positive charge that's present, or alternatively, the number of protons that you can find in the nucleus. It also handily identifies exactly which element we are talking about. Oh no! This slide contains many a mistake. Why don't you pause it here and work through the examples and try and figure out why are they wrong? To understand why isotope notation might be really powerful to us requires us to first gain an understanding of what an isotope might be. Frederick Soddy and Winifred Bealby were the first people to really understand what it meant to be an isotope. They were looking at various different substances and realised that it was possible that you could get a heavier version of the same element. It just contained more neutrons. In fact, having more or less neutrons was just one of those accepted differences that you could find within any given element. And so, what are the basic rules about isotopes? First of all, they would have the same atomic number. Switching isotopes doesn't mean you change from one element to another. You are still the same element as before. But what is different is you have a different mass number. Because remember that the mass number was equal to the number of protons added to the number of neutrons. If you change the number of neutrons, then the mass number, the number at the top of the isotope notation, is also going to change. The curious thing about isotopes is that they are chemically very, very similar, if not exactly the same. It means you could switch in or out a heavier or lighter version of the same element, and that element would still get up to all of the same chemical reactions as any other isotope of that same element. So maybe this might help. Here are 3 different isotopes of carbon: carbon 12, 13 and 14. Notice about them. The atomic number is 6 in all 3. That means they always have 6 protons. It is always carbon. And also notice that the number of electrons in those 3 diagrams is the same each time. They're still all having 6, which perfectly balances the 6 protons and makes it electrically neutral. What changes each time is the number of neutrons. So carbon 12 has a mass number of 12 because it has 6 protons and 6 neutrons. Carbon 14 has a mass number of 14 because it has 6 protons and 8 neutrons. And the interesting fact here is the origin of the word isotope. It comes from the Greek word isotopos, which means same place, because the isotope can exist in the same place on the periodic table or as a molecule. If you think about the fact that isotopes will undergo the same chemical reactions, you could have an isotope of your element replacing any of those atoms and it would make no difference at all. It could very much exist in the same place. So what about ions? Well, if there are the same number of positive and negative charges, then your atom is electrically neutral and not technically an ion. But if there was a disbalance, say you didn't have as many protons as electrons, then there'd be more negative charge than positive charge. That would make a negative ion. And a negative ion is called an anion. Now, if it was the other way round, there was more protons than electrons, then it would form a positive charge, and it would be a cation. Now, in isotope notation, we identify these by placing a small plus or minus in superscript after the chemical symbol. So we can see some examples on the left here. Chlorine Cl minus, that has got one more electron than it has protons. Notice that the Cl has 17 protons, that's the atomic number. It means it must have 18 electrons. So if you feel ready, why not have a go at some of these questions and test your knowledge?